everyone. Good morning. My name is Nuria. I'm one of the organizers of the school. It's great to have you all here. It's great to have all you here. We have the video streaming for the online participants on as well. And let's kick off the school with nice lectures from Ronald.
My name is Nuria. I'm one of the
University of Amsterdam.
It's
great to have you all here.
Who tell us
about introduction in quantum computing, and
it's
later
great to have
all you here. We
Pages
have
of
the
this.
video streaming for the online participants on as well. And let's kick off the school with nice lectures from Ronald.
My name is Nuria. I'm one of the
University of Amsterdam.
It's
great to have you all here.
Is this on? Like it's working well?
About introduction in
well?
quantum
Okay.
computing, and
It's
later
great to have
all you here.
Okay, so this, these are going to be lectures about first the model of quantum computing and then sort of the basic algorithms. In particular, tomorrow I will discuss Schwarz algorithm for factoring.
to have you all here.
Is this on? Does it work? Search well?
About
Reasonably
introduction in
well?
quantum
Oh, I'm
computing,
sorry.
and later to have all you here.
1, 2, 3, yes. Okay, so this, these are going to be, we'll do some lectures of introduction today, the model of quantum, probably already a little bit then sort of the basic algorithm. And tomorrow I'm going to Schwarz algorithm discuss Schwarz algorithm for factoring. Search this on. It was much more ambitious initially. I was well. Oh, I'm sorry. Hamiltonian simulation. Okay, so this, these are going to, we'll do some lectures of introduction. If you want to read more, probably already a little bit then the basic algorithm. And tomorrow I'm going to as well. Schwarz algorithm for factoring. Search this on. We also encourage you to interrupt me for questions as well. Oh, I'm sorry. And you should really view. Okay, so this is first we'll do some lectures of introduction. If you want to read more, probably already a little bit then basic algorithm. And tomorrow I'm going to, and this also applies to the people on Schwarz algorithm for factoring. Search this on. We also encourage you to interrupt me for questions as well. Oh, those people can ask questions in Discord. You should really view. Okay, so this first we'll do some lectures of introduction. If you want to read more, I hope it's sort of visible. Tomorrow I'm going to, and this also applies to the people on Schwarz algorithm for factoring. Very surprised that humanities people. We also encourage you to interrupt me for questions as well. Oh, those people can ask questions in Discord. You should probably view. Okay, so this first we'll do some lectures of introduction. If you want to read more, I hope it's sort of visible. Tomorrow I'm going to, and this also applies to the people on Schwarz algorithm for factoring. Very surprised that humanities people. We also encourage you to interrupt me for questions as well. Oh, those people can ask questions in Discord. You should probably view. Okay, so this first we'll do some lectures of introduction. If you want to read more, I hope it's sort of visible. Tomorrow I'm going to, and this also applies to the people on Schwarz algorithm for factoring. Very surprised that humanities people. We also encourage you to interrupt me for questions as well. Oh, those people can ask questions in Discord. You should probably view. Okay, so this first we'll do some lectures of introduction. If you want to read more, I hope it's sort of visible. No problem. Black ones, okay, let me see if those are, thank you. Okay, let me just, in the meantime, do a little test for you people to see which of these pens is the least bad. This one is very bad. Am I doing something wrong? Oh, okay. These are not black pens. This is something to do with chalk. Yeah. It's just something like kreide. Okay, so I'll just use the blue pen, the dark blue pen. Okay, let me just repeat in case this was messed up in the audio. If anybody wants to interrupt me with questions, either from you guys here or from the people online, please do. Okay, so let's get started. So this is supposed to be sort of your first introduction to quantum computing, though I suspect that many people here have seen some of this stuff before. So I'll go a lot quicker than I would go in my master's course, so that we can get down to more interesting things, even within this hour already. So what is quantum computing? You can think of quantum computing as sort of the merger of two of the most important developments of 20th century science, one being quantum mechanics, which was developed between roughly 1900 and roughly 1925, including here in Zurich. In fact, this year sort of commemorates 100 years of the completion of quantum mechanics around 1925. And the other development is computer science, which started theoretically in the 1930s by the work of Church and Turing and these people. And of course has taken an enormous flight since then, right? You all have a massively powerful computer in the form of your phone. And these two sort of strands of science, they combined in the 1980s to form the field of quantum computing, where the idea is, let's try to use all the weird effects that quantum mechanics gives us, let's try to use those to improve computing, right? And not improve computing by making it 10% faster, but improve computing fundamentally in the sense that you can really do different kinds of computation than you could do before, right? And that's what I'll try to explain to you. And in order to start somewhere, let's start with the basic unit of information of the classical computer, which is a bit. And what is a bit? It's a 0 or a 1, right? So you can implement this in transistors, and your transistor is supposed to be a 0 or a 1, and if it's somewhere in the middle, your transistor is broken. So logically speaking, theoretically speaking, and my lecture is really from a sort of the perspective of theoretical computer science, I'm not going to do physics, but theoretically speaking, a bit is just some variable which can have a value 0 or 1. And what is a quantum bit? In some sense, a quantum bit is 0 and 1, though I think this is super misleading, so let me put the word and in quotes. And let me tell you what this word and means. So a qubit is typically denoted with these funny signs around it. This is called cat notation due to Dirac. And what does this mean? So this is a way to embed bits and quantum bits in linear vector spaces. And you should think of this here as a basis vector in a two-dimensional vector space. And you should think of this here as another orthogonal basis vector in that same two-dimensional vector space. So we typically associate a qubit that has value 0, we associate it with the vector 1, 0, and we associate cat 1 with the vector 0, 1, right? These two vectors together, they form a very reasonable basis for the two-dimensional vector space. And then what is a qubit? A qubit is really a linear combination of these two things, right? And thanks to the fact that I've embedded these qubits in a vector space, I can just take linear combinations of them with real or even complex coefficients. So I can multiply these two vectors with complex coefficients. This would be called the amplitude of the basis state cat 0. This would be called the amplitude of the basis state cat 1, right? And these are vectors, you can just add them up. That's what the word and in quotes refers to. You can take linear combinations of classical possibilities. And what you get from this is just a simple vector with the amplitudes. And this is an element of C2, the two-dimensional complex vector space. Am I writing big enough for the people sitting at the back? If not, please complain. Okay, now keep going like this. Right, so the word and really refers to taking linear combinations. And you will see soon that these amplitudes here, they cannot be arbitrary. They're somewhat restricted. In fact, if you have many of them, then most of them are kind of small. We'll get to that in a second. Let me give you some examples. So a simple example is the special case where the two amplitudes are real numbers. And in that case, you can picture your qubit nicely in a two-dimensional picture where the two axes correspond to the two basis states. So the horizontal axis corresponds to ket 0, the vertical axis corresponds to ket 1, and your qubit would be somewhere in the middle. In fact, it will have unit length, as you will see in a moment. So for instance, if this angle here is theta, then the state of this qubit, it would be cosine theta ket 0 plus sine theta ket 1. And there are multiple things you can do with qubits. You can operate on them in certain ways, but you can also measure them, just like you can measure a classical bit. And if you measure a qubit, what you will get is something weird. Namely, the amplitudes will sort of collapse to something simple. So measuring a qubit, let's say we have a qubit which is in a state alpha 0 ket 0 plus alpha 1 ket 1. What will be the outcome of your measurement will be a classical bit, 0 or 1. And quantum mechanics does not tell you what the outcome will be, but it gives you the probability distribution. So the measurement outcome is going to be 0 with probability given by the squared magnitude of the associated amplitude, so alpha 0 squared. And the outcome is going to be 1 with probability modulus of alpha 1 squared. And this already tells you something about these amplitudes, namely the sum of squares of the amplitudes has to be 1. Otherwise, this is not a well-defined probability distribution. Right? So corollary of how these measurements work is that ket alpha 0 squared plus ket alpha 1 squared is equal to 1. Right? You may have noticed that I drew this state here on the unit circle, and this is not a coincidence. Sum of squares of amplitudes is always 1. Otherwise, this probabilistic stuff doesn't work. So the vector of amplitudes is a unit vector, vector of length 1. I will sort of massage this part of the board later when we talk about more than one qubit, but for now we're just talking about one qubit because that's really the simplest case to start with. Make some space here. Oops. Right, so measuring is one thing you can do with your qubits, but you can also do a so-called unitary operation on it. And quantum mechanics says that the operations you can do on your vector of amplitudes are linear. Operations on quantum states, operations which are not measurements, so any other operations. Are linear. And that just means you multiply your vector of amplitudes with some matrix to get the vector of amplitudes of the new state. And there's something useful here, which is that, if you start with a certain quantum state, it must obey this relation here. The sum of squares of the amplitudes has to be 1, otherwise the probability interpretation doesn't make sense. And the same should still be true after applying a unitary operation, because the new quantum state that you get then, it should still make sense if you measure it. The sum of squares of the new amplitude should still be 1. And that means that the specific linear operations that quantum mechanics allows are the ones that preserve the length. So not only are these operations linear, they're also length preserving. So vectors of length 1 should map to vectors of length 1. And linear algebra has a nice name for matrices that are both for matrices that are length preserving, namely those are the unitary matrices. Typically denoted by U. And mathematically, the property that makes a matrix unitary is that it has an inverse, and this inverse equals the conjugate transpose of the matrix. So U inverse equals U star. And so this star notation here, this is mathematician's notation, which I will follow for the conjugate transpose of a matrix. So you conjugate it, you transpose it, and you conjugate all the complex entries. And physicists would write this as U dagger. Actually, let me just gauge how many of you are physicists and how many of you are non-physicists. These are the physicists. Okay, so for you people, this is the dagger. But I will typically denote it by star because I also in my lecture notes, I'm sticking to the mathematics convention rather than the physics convention. So these are the kind of operations that quantum mechanics allows us to do. Now, in the simple case of one qubit, we're just talking about a two-dimensional vector space. So really, these matrices are 2x2 matrices. Let me just write some of the more important ones on the board. So examples of single qubit unitaries. So unitaries that act on only one qubit. Maybe a question to you, what is the very simplest unitary you can do on a qubit? Mathematically simplest, at least. Identity, exactly. Right, so that's an example of a unitary. Kind of a trivial one, but it is there anyway. And you might think, who cares about the identity? But it's actually super important physically to be able to implement the identity, because doing an identity means that your qubit is not disturbed by noise. Right? This is not a physics course, what I'm teaching here. But if you are actually implementing qubits and quantum operations in a physical system, let's say electrons or photons or whatever kind of two-level system you want to use to build your qubits on, there will be noise, there will be errors, and doing the identity operation is actually a very hard operation because it means preserving your qubit. Doing nothing is very hard in practice. Doing nothing is very easy for mathematicians, fortunately, which is why mathematicians have a reputation for being lazy. Okay, this is a still very simple, but no longer identity map. This is the X gate, also known as the NOT gate. And what this does is this flips ket0 and ket1, right? You can see that this basis vector here would be mapped to this basis vector here and vice versa. So just like the classical logical NOT operation, this flips a logical 0 and a logical 1. Right? And in superposition, you can also think of it as swapping these two amplitudes. Alpha 0 becomes alpha 1 and alpha 1 becomes alpha 0. There's the Z operation. What this does is it leaves the basis state ket0 alone, and it maps the basis state ket1 to minus itself. And a different way to think about that is if you apply the Z gate to a vector of amplitudes like this, the alpha 1 gets a minus sign in front of it. These signs are also known as phases sometimes. Another important gate is a rotation gate, let's say over an angle theta. So this is denoted as cos theta, with theta some number between 0 and 2 pi, sine theta and minus sine theta. If you want to check, by the way, that the given matrix is unitary, often the easiest way to do it is to check that each column is normalized, length 1, and that the columns are pairwise orthogonal, which in this case is very easy to check, right? Cosine squared plus sine squared is always 1. And if you look at the inner product between this column and this column, that's going to be 0 because of this minus sign here. And why is this called a rotation matrix? Because it sort of rotates a qubit like this. If you apply this r theta to ket 0, you get this qubit. If you apply it to ket 1, you get like this. So it rotates over an angle of theta. Of course, this interpretation also makes sense if your qubit has non-real, like really truly imaginary amplitudes, but it's nice to illustrate it in the picture where the amplitudes are real, because there really is a rotation. Another important gate, especially for people who care about error correction, is the so-called T gate, which looks like this, e to the I pi over 4. This is something that adds a complex phase to the ket 1 basis state, namely e to the I pi over 4. Notice that if you take t to the power 4, you actually get this gate. So these gates are not independent from one another. There are relations between them, and we'll get back to that later. And the last and maybe most important single qubit gate that I want to write down is the Hadamard gate, which is this one here. And this is a gate that allows you to create uniform superpositions, right? Sort of, you should think of this as sort of like a quantum version of a coin flip, because if you apply it to the 0 qubits, you get a uniform superposition of ket 0 and ket 1 with amplitudes 1 over root 2. And if you apply it to ket 1, you get the same thing, but with a minus sign in front of the ket 1. Can people still see if I write this low? It's troublesome. Okay, I'll try to write no lower than this. Right, and notice that if you look at this sort of axiom of what measurement does, then if you measure this qubit here, you get a 50-50 distribution between outcome 0 and outcome 1. If you measure this qubit here, you also get a 50-50 distribution between outcome 0 and outcome 1. And it seems as if this minus sign here actually doesn't do anything. And this is true. Like as soon as you start measuring, like these phases on the amplitudes, they become irrelevant, because really probabilities are determined by the absolute values of the amplitudes. So you might think, who cares about these minus signs? But one thing that I really want to sort of get across in these lectures is that these minus signs are the most important thing in quantum states, because they allow interference effects. They allow sort of positive and negative amplitudes to sort of cancel each other out in a similar way as how different waves that are out of phase, if you put them on top of each other, they can partially or fully cancel each other out. And I want to illustrate this here with your very first little baby quantum algorithm, where you can already see a little interference effect happening. Right, so this is a little baby algorithm. It's a baby algorithm because it only works on 1 qubit. But it's kind of nice that after, I don't know how long I've been talking now, but maybe after, I don't know what's, maybe 20 minutes or so, you can already see your first quantum algorithm. And it's sort of a toy algorithm. It doesn't really do anything very important, but it will very nicely illustrate how superposition, which is like linear combination of basis states, and interference effects, which is like positive and negative amplitudes canceling each other out, how those collaborate to do computations that you cannot do in the classical world, in classical physics. And this is usually called the Deutsch algorithm, though it's really done by David Deutsch and with some additions and simplifications by others later. Let me just call it the Deutsch algorithm. David Deutsch was one of these people who sort of put quantum computing on the stage in the mid-1980s. And the idea here is that somehow we are given 2 input bits, let me call them A and B, and they are plus minus 1 valued. So there's 2 input bits. A comma B. And each of them is a plus or minus 1. And the very simple computational question we want to solve here is the question, are these 2 bits equal or not? So is A equal to B? Right, and this, of course, very easy to do on a classical computer. You know, you look at A, you look at B, and you see if they're the same or not, right? Easy peasy. But you would have to look at A and B separately. And somehow the baby quantum algorithm that I'm going to explain avoids that by looking at A and B only once, but in a superposition, instead of separately looking at them. So here's the baby algorithm to answer this question, to determine if A is equal to B or not. And I'm going to assume that we can access these bits by a unitary operation that sort of allows us to get A and B in the phase of ket 0 and ket 1 respectively. So assume we can do an operation which I'll sometimes call an oracle, which looks like this. It's a single qubit operation, right? Unitary, so it has to be a 2x2 matrix. And the 2x2 matrix that I will allow myself to do is this one. It has A and B on the diagonal. A and B are plus or minus, so this is clearly a diagonal unitary matrix. And I'm just allowing myself to access the two input bits in this way. And if you don't like that, just dispense your disbelief, right? I'm not trying to explain you something realistic here. I'm trying to explain you your very first baby example of how superposition and interference effects can collaborate to do interesting computation. Okay, so here's the algorithm. And algorithms in quantum computing are typically written in the form of a circuit where on the left you have your initial state, and then the circuit sort of tells you which gates to do on which qubits at which point in time. We are still in the situation where we have only one qubit, so this is going to be a very simple circuit. So I'm going to start with a qubit which is like in the classical state 0, like a classical bit 0. Then I'm going to do a Hadamard gate, creating a superposition. Then I'm going to do my funny operation O for oracle. If you don't like it, just suspend your disbelief for now. I'm going to do another Hadamard gate. And I'm going to measure. Right, so this symbol on the right here, this denotes measurement. Measurement in this sense here, that you will create a probabilistic collapse of your qubit. And I claim that this very little algorithm here, this actually perfectly will tell me whether or not A equals B or not. And the nice thing here is that we didn't separately look at A and separately look at B. We only looked at these bits in a superposition, as you'll see right now. Right? Let me just be clear that time in this picture progresses from left to right. You start here, and you do these operations in sequence, and you do a measurement at the end. And if you want to sort of analyze what a quantum algorithm does, and the algorithm is given to you in the form of a circuit, your best bet to see what it does is usually just to sort of track the state as it goes through the circuit. So let's do that and see that an interesting outcome comes out. Tracking the state. So we start with ket 0. Right, this is on the left of the circuit. And we apply a Hadamard gate. And we know what that does because I wrote it down for you here. It just creates a uniform superposition over the two classical bit values, ket 0 and ket 1. So if you do a Hadamard, you get 1 over root 2, ket 0 plus 1 over root 2, ket 1. Right? We are now here in the circuit. We did the first Hadamard operation. And now I'm going to apply my magical oracle, which gives me access to these bits A and B in the phases. So I'm applying the O operation. And what do I get? I get 1 over root 2 times A, which is plus or minus 1, ket 0, plus 1 over root 2 times B times ket 1. And that is, now we are here in the circuits. We did the operation O. If this is not visible or otherwise hard to understand, please stop me. Okay, so now the last thing that the circuit tells us to do before the final measurement is to apply another Hadamard gate. And here you will see the interference effects happening. So far, the only thing we did was create a superposition, but the second Hadamard gate is going to create the interference effects. So pay close attention what will happen now. So I'm going to do my second Hadamard gate on this thing here. And what does that do? Well, this will be slightly more complicated, but we know at least what it does, what the Hadamard gate does to ket 0 and ket 1, because I wrote it down for you here, so we can just fill that in. Everything is linear here, right? So if I know what happens to ket 0 and I know what happens to ket 1, I know what happens to any superposition. So I'm going to get now 1 over root 2 times A times the effect of applying Hadamard to ket 0, which is 1 over root 2 ket 0 plus ket 1, plus the same thing for the other part of the superposition. Okay, and this looks kind of messy and complicated. But let's try to regroup this by bringing together all the amplitudes sitting on ket 0 and all the amplitudes sitting on ket 1. Right, so I can rewrite this guy here as, so let's gather first all the amplitudes sitting on the ket 0 basis state, right? So that's this piece here plus this piece here. So this is 1 over 2 A plus B ket 0. And let's gather the amplitude sitting on the ket 1 basis state. So this is 1 over 2 A minus B ket 1. And now sort of a little miracle occurs depending on whether A and B were equal or not. So the amplitude of ket 0 here, what happens if A and B were the same, either both +1 or both -1? Question to you. Yeah, so with the 1/2 in front, it would actually be 1, and it could be plus or -1, right? It could be that A and B were both -1, or it could be that they're both +1. So really this underbrace thing here is plus -1 if A is equal to B. And what would it be if A and B are different? If one of them is +1 and the other one is -1, it actually becomes 0. This is an example of interference. Okay, I'm writing lower now than I promised to. I apologize for the people in the back. I hope you can still see it. The main thing is that now this amplitude here is plus or minus 1 in case the two bits are equal, and it's 0 if the two bits are distinct. So what does that mean for our measurement outcome here? This measurement outcome is going to be 0 if the two bits are the same, and it's going to be non-zero, meaning ket 1, because then all the amplitude is sitting here, if A and B are different. Right, so this measurement outcome here, it tells us with certainty, no error probability, whether or not A and B were equal. Right, and this is a trivial computational problem, but we sort of solved it in an interesting way by not separately looking at A and separately looking at B, as a classical algorithm would do, but sort of creating a superposition, and part of my superposition looks at A, and part of my superposition looks at B. And then these sort of amplitudes are reassembled in the interference effects that are caused by this Hadamard transform. Okay, so this was your first algorithm. And many of the later algorithms are of a very similar flavor. They set up a superposition, they induce some sort of nice interference effects, you sort of calculate the probabilities in the final state from the final state, and the output distribution gives you useful information about the problem you're trying to solve. Okay, so this is what I wanted to say about the whole frame of just one qubit. And if there's now no further questions, then I will move. Thank you. Please. Yeah. Two basis states.
Basis states, but in this algorithm, you say you have two kind of states. You might not know what to say. So
no, but I think you're using the word state ambiguously here. You should think of this as input bits, classical input bits. These are not quantum states. Like we will typically look at algorithms that start with a classical input, for instance, a number that you want to factor, and it does quantum stuff on it, and some classical output comes out. Right, so these are the inputs. They're classical, but you have some sort of funny access mechanism to them in the form of this unitary O. Yeah. That's right. And maybe you don't believe that such a device exists. That's totally fair. I'm just trying to illustrate the principle of how superposition and interference can collaborate to do interesting things. Right? But the input is classical here, and the output is classical as well, because the measurement outcome at the end of the day is just a classical bit. And in the middle, quantum stuff happens. Thanks for the question. Okay. Moving on to 2 bits and qubits. Okay, so let me try to sort of be clever and massage the board a little bit here so I don't have to erase everything. So what is the situation with 2 bits? There are now 4 possibilities. There's 0, 0, 0, 1, 1, 0, and 1, 1. Right? These are the 4 possible situations you could have if you live in a 2-bit world, which is not a very interesting world, but it is what it is. Right, so this 2-bit system has 4 possibilities. And in the quantum case, you also have 4 basis states, which would be ket0, tensor ket0. I'm going to explain this notation in a second. Ket0, tensor ket1. Ket1, tensor ket0. And ket1, tensor ket1. Okay, I guess I have to erase this stuff anyway now, most of it. So let me first explain to you what this notation means here. So this operation here, like a cross, like an X with a circle around it, this is the tensor symbol, also called the Kronecker product, and there's different names for this thing. It's called tensor product in quantum mechanics and in quantum computing. And it's a way to combine low-dimensional vectors or matrices into higher-dimensional vectors or matrices. And let me just show you how this works. So, for instance, let's look at the basis state corresponding to ket0, tensor ket0. What does that mean? We know what is ket0, right? It is this vector here. And what does the tensor product do? So sort of operationally, the way you can think about a tensor product is you take the first vector and you multiply its first entry with the second vector, and you also multiply its second entry with the second vector. So if you take this thing here, what you will get is 1 times the vector 1, 0, 0 times the vector 1, 0, which is equal to 1, 0, 0, 0. Okay, this is kind of ugly notation. I think mathematicians will hate this. Don't try this at home. I'm just trying to sort of explain to you operationally how tensor products work. Right, so quite naturally, using this tensor product way of combining 2-dimensional vectors, you get a 4-dimensional vector, namely this one. And the same is true for all the other 4 basis states. For instance, this guy here, if you do the same tensor operation, it looks like this. This guy here looks like this. And this guy here, well, let me not write it because of lack of space, but you sort of see the principle. You very naturally get the standard basis of the 4-dimensional vector space. Ket0, tensor ket0 is this vector. Ket0, tensor ket1 would be the vector 0, 1, 0, 0. Ket1, tensor ket0 would be this vector, and ket1, tensor ket1 would be this vector. So you very naturally get the standard basis for the 4-dimensional space. And like before, you can take linear combinations of these 4 basis states with 4 coefficients, which are called amplitudes. So you're going to have alpha 0, 0 being the amplitude of the first possible basis state, alpha 0, 1 being the amplitude of basis state ket0, ket1. I will also sometimes write this thing, by the way, as either 0, ket0, ket0, or even if I'm super lazy, I'm going to write it as ket0, 0. So this is really just shorthand for this, and this is really just shorthand for this. But you don't want to write this tensor symbol all the time. So we will typically sort of contract different basis states by concatenating the sequences of bits. Right, this is just shorthand. It saves some writing. Okay, let me continue with the possibilities here, the 4 basis states. And what is this? This is funny cat notation, but really, because these 4 basis states correspond to the standard basis of the 4-dimensional vector space, this is also just the same as the vector of the 4 amplitudes. And for the computer scientists here, like the way it's done here very naturally leads to so-called lexicographical ordering of the different bit strings here. There are 4 different bit strings here, 0, 0, 0, 1, 1, 0, 1, 1, and I'm ordering them in so-called lexicographical ordering, which is also the ordering that you would get if you would interpret these things as integers written in binary. Those integers would be 0, 1, 2, and 3. If you've never heard about this binary notation, don't worry about it for now. But in any case, this is how you set up a 2-qubit system, a system of 2 qubits, and the state is described by a vector of 4 amplitudes. And you can sort of extrapolate yourself how this goes with 3 qubits. With 3 qubits, you would have 8 basis states, and the vector of amplitudes would be an 8-dimensional vector. And so this is a vector, in this case, element of C4. In the case of 3 qubits, it would be an element of C8. In the case of 4 qubits, it will be an element of C16, etc. You sort of see how this goes, right? And an important thing here is that the number of amplitudes goes up exponentially with the number of qubits, which means that if you have a moderate number of qubits, like 100 or 200 or so, the dimension of the vector of amplitudes needed to describe that system is already humongous. 2 to the power 200 is humongous. It's sort of comparable to the number of particles in the universe. But 200 qubits is not a lot, right? You can have a sequence of 200 electrons, at least in theory you can imagine that. And somehow describing the state, the potential state of such a thing, it takes an enormous amount of space if you were to write out the vector. And of course, nature doesn't actually write out this vector. Nature sort of implicitly keeps track of the vector of amplitudes. Okay, so this is a description of a state of 2 qubits. Measurement kind of works in the same way. If you're measuring a 2-qubit system fully, then you get outcome 0, 0 with probability given by its amplitude squared. And the same is true for the other 3 options, right? For instance, you get outcome 1, 1 with probability given by alpha 1, 1 squared. And again, you must have the property that the sum of squares of the amplitudes is 1, otherwise this probabilistic interpretation makes no sense. And there's something that I neglected to say when I was talking about 1 qubit, namely what happens to the state after you get a measurement outcome. And what actually happens is that the state has collapsed by the act of measurement to the measurement outcome, right? So in the case of 1 qubit, you can start with this fancy superposition. Maybe alpha 0 and alpha 1 are like super complicated numbers, with infinitely many digits, etc. If you measure it, you're going to see a classical 0 or 1, and the state will collapse to that basis state that you saw. If you got measurement outcome 0, the state is going to collapse to ket 0. If you got measurement outcome 1, the state is going to collapse to state ket 1. And all the information in the amplitudes is lost. This is a very destructive act to measure. And typically quantum algorithms, at least in a non-noisy setting, typically quantum algorithms only do the measurement at the very end, because you don't want to destroy your amplitudes in the middle. Now, if you have a 2-qubit system, you could ask a reasonable question: what happens if I measure only 1 of the 2 qubits? right? You could have like two physical systems, let's say two electrons. You could choose to only measure one of them. What happened in that case? So what I wrote here is measuring a 2-qubit system fully, like measuring both of its qubits. If you measure only the first qubit, measuring the first of 2 qubits, so what's going to happen in that case? In that case, you will get a measurement outcome for your measurement of the first qubit, a 0 or 1, and you'll get a collapse, but not necessarily to a basis state in the second qubit. So let's say we have a 2-qubit state like this, right, with amplitudes alpha 0, 0, alpha 0, 1, alpha 1, 0, and alpha 1, 1. And what would happen if you only measure the first qubit? So a reasonable guess is that the probability of seeing outcome 0 here should be this, the sum of squares of the amplitudes corresponding to states that have a 0 there. And this is indeed the case. So you get outcome 0 with probability given by the sum of alpha 0, 0 squared and alpha 0, 1 squared. Notice that this is actually the marginal probability of seeing 0 if you were to measure both of the qubits. But in this case, you get a collapse not to a classical state, but to the remaining superposition that is kind of consistent with this measurement outcome. So you measured only the first qubit, you saw outcome 0. 2 of the 4 basis states are consistent with that outcome, namely this guy and this guy. And your state is going to collapse to a superposition of those two. So you collapse to alpha 0, 0, get 0, 0, plus alpha 0, 1, get 1, 1. And this is the time for you to sort of get angry and protest. What is wrong with what I wrote here? It's not normalized exactly. So the way to make this a norm 1 vector, again, is just to divide it by its norm. Somehow nature does that. It kind of partially collapses the state. It kind of readjusts the amplitude so that the whole thing is norm 1 again. But we have to divide this by the square root of the sum of squares of those two amplitudes. Right, so this is what measurement does for a 2-qubit system, and you can generalize yourself what happens if you have a 3-qubit system or a 4-qubit system or even an n-qubit system. Any questions about this? It's starting to get a little bit subtle here. In fact, if you let philosophers talk about this, they will go on for decades to discuss what this actually means. We don't have time for that. There was a question?
Yeah, say you measure single qubit, and then like say you got state of 0. Can you then, we'll say, apply a Hadamard to that and put it again in superposition?
Yes. Yeah, so I was asked to repeat the question if they come from the room. The question is, if you measure the first qubit, and you get some classical outcome, 0 or 1, can you later put that in superposition again with a Hadamard gate? And the answer is yes. At least in my theoretical model, it is. Like in some physical systems, measurements really sort of demolish the system. And in that case, you can't do anything with it anymore. But mathematically speaking, it's totally fine. You collapse to, let's say, Cat1. Feel free to do whatever unitaries on this thing later. Thanks. Other questions? Yes, please.
One is 0, 1, 1.
The second one where?
Collapses to alpha 0, 0.
Oh, sorry. So yeah. Yeah, absolutely.
Yeah.
Thank you very much. That was just a typo.
Yeah.
It should be 0. Yep. Thanks. Thanks. Anybody, if I make a mistake, please tell me. I'm sure I'm going to make mistakes. Okay, so this is about measuring a 2-qubit system, and we can also talk about doing unitary operations on a 2-qubit system, which we need to do if we want to do clever computation. Because if you only do single qubit operations, you never actually interact different qubits with one another. And the most important gate on 2 qubits is the so-called controlled NOT gate, which applies the NOT gate to the second qubit of a state if the first qubit is in state 1. So 2-qubit gate so-called controlled knot or C knot. And you know, this is now a 4x4 matrix. It could be applied to any superposition, but thanks to linearity, it suffices for me to tell you what it does on the 4 basis states, because then by linearity, you know what happens to any possible superposition thereof. And the controlled NOT gate, what it does is it maps ket 0, 0 and ket 0, 1 to themselves. You should think of the first bit here as a control bit that determines whether or not the X gate is happening on the second bit. And if the first bit is 1, meaning the control bit is on, then actually the X gate is applied. So you can sort of think of this as an if-then operation, at least when you look at its application on basis states. If the first bit is 1, flip the second bit. If I write this as a matrix, it looks like this. It's a 4x4 matrix because it's a 2-qubit operation. So as a matrix, it looks like this. Like this is just the matrix representation, the 4x4 matrix representation of this map on the 4 basis states. Right, and it all looks pretty classical. It is very, very classical, right? You can really think of it as a classical if-then operation if you apply it to basis states. But you're allowed to do this also on superpositions, and that's why this can have like big quantum effects. Let me check the time. What time should I stop, sort of? 8 minutes, okay. Okay, so then, okay, so this is what I wanted to tell you about multiple qubits, right? And I only talked about 2 qubits, but you can generalize it yourself to 3, 4, 5, up to n qubits, whatever you want. I hope the principles are kind of clear, right? Whenever you have an n qubit system, its state is described by a vector of 2 to the n complex amplitudes, 1 for each possible basis state. If you measure it, you get this probabilistic collapse, where somehow the amplitudes square and become probabilities. And you're also allowed to do length-preserving unitary length-preserving operations on your vector of amplitudes. So to end this first hour, let me say a little bit about entangled states, just as a way to illustrate what we just did with 2-qubit systems. So I'm now going to draw a little circuit for you, which acts on 2 qubits. It's a very simple one, right? Time always goes from left to right in these pictures. So on the left, we have our initial state. Let's say it's 2 zeros. Then I'm going to Hadamard gate on the first qubit. And I'm going to do a controlled NOT gate on the pair of qubits. And I'm just going to see what comes out. By the way, these controlled operations are also sometimes written in the literature as sort of having a big dot on the controlling bit, and then only the operation that is controlled on the second bit. So let me write that in the more common notation as well. So this notation here, this really means the first bit controls whether or not this X gate is applied to the second qubit. So this block here, this is a controlled NOT operation. Now let's just see what state comes out here. Right? And if you want to see what state comes out here, the easiest thing is just to sort of to track the state as it goes through the circuit. So we start with 0, 0. And we apply a Hadamard gate to the first qubit. Right? And if you look at this time step here, what really happens is you do a Hadamard gate on the first qubit and you do identity on the second qubit. So the overall unitary that you do would be H tensor identity. And what this does is nothing happens to the second qubit, identity gate is applied to it, but the first one, a Hadamard gate, is applied to it, so you get 1 over root 2 ket 0 plus ket 1, tensored with ket 0 on the second qubit, which is the same as 1 over root 2 ket 0, 0, plus 1 over root 2 ket 1, 0. And now the circuit tells us to apply a controlled NOT gate to the 2-qubit state that we have. And maybe somebody can tell me what comes out. What's the state that comes out if you do a controlled NOT gate here? Exactly. It's 1 over root 2 ket 0, 0 plus 1 over root 2 ket 1, 1. Right, because if you look at these two basis states here, in the first one, the control bit is off, it's 0, nothing happens to it. In the second basis state here, the control bit is 1, so the second bit gets flipped. It goes from a 0 to a 1, and this is the state that you get. And this is a state of fundamental importance. This is the so-called EPR state, Einstein-Podolsky-Rosen. And this is sort of the canonical example of a 2-qubit state that is entangled. And entangled means it cannot be written as a product of a state on the first qubit tensored with a state on the second qubit. So this is entangled. Cannot be written as, some state ket phi for the first qubit, tensor ket psi for the second qubit. There do not exist qubit states ket phi and ket psi whose vector of 4 amplitude is the same as this vector of 4 amplitudes. Yes, please.
Just to be sure, we
Yeah.
just omitted the tensor product symbol, for instance.
Here and here.
Yeah, or at
Yeah.
the beginning.
Also here, yeah.
Yeah, okay.
Yeah. So this is the same as this, and is the same as ket 0 tensor symbol ket 0. This is just the shortest way to write it. And if you get into more qubits, it becomes terribly painful to write the tensor symbol all the time. So you should allow me and also yourself to be lazy with these things. Maybe to end this hour, let's actually do a proof that this state here is entangled. All right, so you can think of this as a theorem, little theorem, that this state here cannot be written as some tensor product of a separate state for the first qubit times a separate state for the second qubit. So let me prove that. Assume, towards a contradiction, that there exists 2 amplitudes alpha and beta for this guy and 2 amplitudes gamma and delta for this guy, such that the tensor product gives you exactly the vector of 4 amplitudes that you have here, right? Just to help you to write this as a vector of 4 amplitudes, it looks like this. So I'm telling you that this vector of 4 amplitudes cannot be recreated by taking a tensor product of something for the first qubit and with a separate thing for the second qubit. So assume that there exists alpha, beta, gamma, delta. Alpha and beta would be the amplitudes of this guy. Gamma and delta would be the amplitudes of this guy. Such that alpha, beta, tensor, gamma, delta would equal the amplitude vector of the EPR state. So what is the left-hand side here? If I write out the tensor product and I do that here, then the vector of 4 amplitudes would be alpha times gamma, alpha times delta, beta times gamma, beta times delta. Now, if you want equality between this 4-dimensional vector and this 4-dimensional vector, then in particular alpha delta has to be 0 and beta gamma has to be 0. Right, so alpha times delta has to be 0, which implies that alpha is 0 or delta is 0. Also, beta gamma needs to be 0 because of equality in the third line of the vector. I guess I'm writing too low, I'm sorry about that. Beta is 0 or gamma is 0. But you know, if alpha is 0 or delta is 0 and beta is 0 or gamma is 0, then actually the first and the last entry, at least one of them has to be 0 as well. Which shouldn't be, because we're trying to recover this vector here, which has non-zero entries in at the top and the bottom of the vector. Right, so this shows you that this simple state here is actually an entangled state. And I'm not going to talk about it, but if you talk about things like quantum games and other things, entanglement has tons of very interesting non-classical properties. In fact, the Nobel Prize was given for a few years ago for experiments involving entangled states and their funny properties. Okay, this is probably a good time to break. Yes? Okay, so break is 10 minutes. 10 minutes. Okay, so let's get back here in 10 minutes and we'll start to talk about slightly more complicated algorithms than the baby algorithm.
Opportunity of So yes,
Continue? Okay, let me switch on this microphone. It should be on again. Everything okay with the Zoom? Okay, so I heard in the break that there was a question in the Discord about how to write maybe the order of the qubits. I'm not completely sure I understood the question, but let me just say that if you have a circuit like this, you know, where sort of the qubits are ordered from top to bottom, then the top to bottom order corresponds to the left to right order when I write things like this. So if I have this will be a basis state where the first qubit is 0 and the second qubit is 0. If this does not clarify the question to the person in the Discord, please ask it again in a different way. Okay, so what I want to do in this second hour is explain two things. One is teleportation, and the other is the Deutsch-Jozsa algorithm. And I'll probably put a little exercise in the middle so that people can test to what extent they understood. In fact, maybe I should do the little exercise first. So the little exercise is a proof of a very fundamental property called no cloning. I switched from a blue pen to a black pen, by the way, hoping that this will be better visible. So in its simplest form, the no cloning theorem, this is a property of quantum mechanics, says there is no two-qubit unitary U that can copy an unknown quantum state. An unknown qubit phi. Right, so phi is a qubit. It's something of the form alpha 0 ket 0 plus alpha 1 ket 1. And I want you to take 5 minutes and try to prove this theorem. So you can prove it by contradiction. So assume towards a contradiction that there exists a unitary such that U, if you apply it to ket phi ket 0, so this is a two-qubit state where the first qubit is phi and the second qubit is 0, that this gives you two copies of phi. And now try to derive a contradiction from this assumption. So I'll give you a few minutes to think about this. Maybe I should say for all. So the same U should work for all phi. Right, so such a U actually cannot exist, and I want you to give me a proof that why it doesn't exist. And one way to do that is to refer back to the fact that this state here, that is an entangled state, but there's also other ways to prove it. I guess this was approximately 5 minutes. Anybody volunteering to give me a proof or an attempt at a proof? Yep.
So either by 0 and by some other, so psi 0, so my psi. Then since U is unitary, it preserves the inner product. And we can say that when we take the inner product of this states, we'll have psi times phi. The right side will have psi times phi squared.
That's right, yeah. So let me repeat that proof on the board. This is one way to do it. I'll write down your proof, and then I'll give my own proof, which relates to this property here. Both are valid proofs. So let's assume that we have two states, two non-orthogonal states. By the way, orthogonal means that the inner product is 0. This is the standard linear algebra notion. Ket phi 0, so that's 1 qubit state, and ket phi 1, that's another 1 qubit state, and their inner product is not equal to, I guess let's assume that the inner product is neither 0 nor 1. So this is not 0 or 1. Then what happens? So U phi 0, 0 should be phi 0 tender phi 0 by this cloning property. Similarly, if you start with phi 1, it should be mapped to 2 copies of phi 1. You can look at the inner product between the states after the unitary, and the inner product would be the square of the inner product between phi 0 and phi 1, because you're getting it in the first qubit and you're again getting it in the second qubit. But before the unitary, so if you compare these two states, so this is the inner product of the 2 qubit states after U. And here the inner product before U actually this is without the absolute value signs. The inner product before the U, because in the second qubit these two states are actually the same, they both have ket 0, you just get inner product between phi 0 and phi 1 once. But the U is supposed to be norm preserving, which is the same thing as inner product preserving. So this number should be the same as this number, which obviously it is not. So that's one proof. Let me give you my own proof, which I like better because it sort of allows me to use properties of entangled states. Nothing wrong with your proof, but it's just different. So I'm gonna let me give people 10 seconds to write this down if they want to. I guess the recordings will also be made public, so there's really, you don't sort of have to like focus all your energy on keeping notes. So I'm erasing this proof. Okay, so an alternative way to prove it is to observe that because this property, this cloning property is supposed to hold for every possible qubit state ket phi, it in particular also has to hold when ket phi is a classical bit, ket 0 or ket 1. Right, so we know that U applied to 0, 0 should be 0, 0. This is what should happen if you're cloning a qubit at 0. And similarly, if ket phi is ket 1, you should end with 2 copies of ket 1. Right, I'm just instantiating this property here that I assumed for the two classical possibilities of ket phi. Ket phi could be ket 0 or ket 1. But now you can apply U to, let's say, a superposition of ket 0 and ket 1. This thing is sometimes called the ket plus state. right? And if you're trying to clone the cat plus state, the qubit which is in the cat plus state, you should get 2 copies of cat plus. Right? This is what happens if you instantiate this phi to the cat plus state. But here you sort of see a problem arising, because what is this state here, this 2 qubit state? This is 1 over root 2 cat 0, 0 plus 1 over root 2 cat 1, 1. Let's apply our purported cloning unitary U to this. Then we know what happens, because we know what U does on cat 0, 0. We wrote it here. And we know what U does on cat 1, 1. We wrote it here. So we get 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. Also known as the EPR pair from up there. Right, and these 2 outcomes should be the same. These are 2 ways to calculate the same thing. Right, now what is wrong here? What is the contradiction that we have obtained? Right, I'm claiming here that these 2 things should be the same, which means that the EPR state is actually the tensor product of cat plus with itself. Exactly, right? Before the break, we actually proved that this thing cannot be written as the tensor product of 2 individual qubits. But this is a tensor product of 2 individual qubits. So they cannot be the same, right? And this is your contradiction. So the assumption that such a cloning unitary U exists leads to a contradiction, and therefore it cannot exist. And this is good to keep in mind. This is very different from classical information, of course. Classical information can be cloned, right? Cloning of classical information, let's say classical bits, is really this operation here, restricted to the case where cat phi is classical, cat 0 or cat 1, right? So you just want a unitary or some operation that does this, and that you never apply to superpositions in the first qubit. And that is actually possible. There is a unitary which satisfies these 2 lines. Maybe somebody can tell me what that unitary is. We've seen it before. It is the controlled NOT gate. The controlled NOT gate does exactly this. You can think of the controlled NOT gate as something that clones classical bits. Classical bits are clonable, and we know how to do it. And even in the quantum world, we know how to do it, because you can just apply the controlled NOT gate. Right? But somehow starting with the sort of being correct for cloning classical bits then leads to a contradiction when you're also trying to clone superpositions. Like it just leads to a contradiction. And then this is a very fundamental property that's also kind of painful, but also intellectually interesting for lots of other purposes. For instance, it makes life very hard if you want to do quantum error correcting codes, because you cannot just copy your information. There's no cloning. So you have to do something more clever. I think somebody else will talk about that later in the week. Yeah. Oh, here. This should be a 0. Thank you. Yep. Yeah, thanks for keeping me honest. I mean, I will probably make 1 or 2 mistakes in every hour, not on purpose. Okay, so this was just a little exercise. Let's go back to the 2 things I want to explain in this hour, which is teleportation and the Deutsch-Jozsa algorithm. So let's talk about teleportation. Maybe I should erase this stuff now. So teleportation is something that's mathematically kind of easy, but philosophically it's quite mind-boggling what's happening. So let's say that there are 2 separated parties called Alice and Bob. You'll probably hear a lot about Alice and Bob. Typically, you know, when there's like 2 different parts of a system or 2 different communicating parties, they're typically called Alice and Bob. And let's say that Alice has an unknown qubit. phi, say alpha 0, ket 0 plus alpha 1, ket 1, that she wants to send to Bob. And she wants to send it to Bob over a classical channel, right? And you can sort of see that this is going to be a little bit painful because this is not a classical object. Right, so as a picture here, there's Alice. Alice has this qubit phi, right? And she only has one copy of it. She doesn't have like the amplitudes alpha 0, alpha 1 written out on a piece of paper. She just has a copy of that qubit. And she somehow wants to send this over a classical channel. To Bob. And at the end of the day, at the end of the protocol I'm going to describe, like Bob should have this qubit ket phi in his hands. Again, not the amplitudes written out of a piece of paper, but just a qubit with those amplitudes. So Bob should end with ket phi. And notice that by the no cloning theorem that we just proved, that means that at the end of the day, Alice can no longer have ket phi, because otherwise we would have made two copies of phi, which we already know is impossible for an arbitrary unknown phi. Right, so somehow Alice will have to lose phi in the process, and you'll see how that happened. Now, you can think about this for a second, and this task is totally impossible. Right? How on earth are you going to do this? How are you going to send it? How are you going to perfectly send one qubit, you know, with its infinite precision amplitudes over a classical channel? Right? Even if I were to allow you like infinitely many classical bits of information to send here, you still can't do it because you don't even know what alpha 0 and alpha 1 are. So totally impossible. Now, what does teleportation do? Teleportation adds a quantum resource to the classical channel. So we're not going to make the channel quantum, that will be kind of cheating, but we're going to let Alice and Bob share one EPR pair. Right, and when I say sharing an EPR pair, what I mean is an EPR pair is a 2-qubit system. What I mean is that Alice has the leftmost qubit and Bob has the rightmost qubit. So for instance, if you look at the mathematical representation of an EPR pair, this basis state would be Alice has a 0, Bob has a 0. This basis state would be Alice has a 1, Bob has a 1. And the whole system would be actually in a superposition of those two possibilities. Right, so sharing an EPR pair means there's like two physical systems, each is one qubit, let's say 2 electrons. Alice has 1, Bob has 1. And the joint state of these two qubits is in this EPR state. So I'm going to let Alice and Bob share this one EPR pair. And notice that the EPR pair has nothing to do with the state phi. The EPR pair is just this. This is what it is. It has nothing to do with alpha 0 and alpha 1. So we're not sort of additionally giving Alice and Bob some shared resource that depends on the qubit that they want to send over. We're giving them something that's independent of ket phi. So now the task is actually possible. So now the task becomes possible. And what's going to happen in the teleportation protocol that I will describe to you now is that the EPR pair that Alice and Bob share will be sort of consumed in the process. The copy of ket phi that Alice has will be sort of consumed in the process. Only 2 bits will go over the classical channel from Alice to Bob, and Bob is going to end up with a perfect copy of phi. Right? And the magical thing here is that somehow these amplitudes here, which are arbitrary, real, or even complex numbers with infinite numbers of bits of precision, they somehow implicitly have been perfectly transferred over a classical channel while only sending 2 bits across the channel. This is kind of a miracle. This is due to Bennett and Wiesner. Sorry, this is due to Bennett, Brassard, a whole bunch of people, Wouters, 6 people that I don't all remember. So this is called teleportation. And let me write down sort of a circuit description of what happens here. And if I want to write down a circuit description of teleportation, then just a sanity check, how many of these wires am I going to have? How many qubits are involved in total? 3, because there's the copy of phi, that's 1 qubit. And there's the EPR pair, which is 2 qubits. And those are the only 3 qubits that will be in play here. So my circuit is going to have 3 wires. And the first wire, the first qubit, is going to be phi. And the other 2 wires, the other 2 qubits, this will be the EPR pair. So the initial state of the joint system of these 2 qubits will be the EPR pair. And because I'm now talking about a system with 2 participants, Alice and Bob, I sort of have to separate the qubits, telling you which ones are in Alice's hands and which ones are in Bob's hands. And I'm going to do this by this dotted line. This dotted line just means the 2 qubits above the line are in Alice's hands, right? Think of it as 2 electrons that she holds. And the qubit below the line is in Bob's hand. So this would be A and B. Right, so this is also, again, what I mean by the EPR pair is shared. The first qubit of the EPR pair is in Alice's hands. The second qubit of the EPR pair is in Bob's hands. Okay, so now I have to tell you what to do to sort of get the phi, which is above the dotted line, so it's in Alice's hands, to get it here in Bob's hands at the end of the protocol. So what are we going to do? We're going to first apply a C0, or rather Alice is going to first apply a C0 between her 2 qubits. Right, both of those qubits are in her hands. They are in her lab, so she can locally do a C0 on those 2 qubits. Then she's going to do a Hadamard on her first qubit. Right, so she has this, she still has the first 2 qubits of a 3 qubit system. The third qubit is still in Bob's hands. And now Alice is just going to measure her 2 qubits. Again, they're in her hands. She can do this locally. It's in her lab, right? Nobody's stopping her. And there will be 2 outcomes, which I'll call A and B. And Alice is going to send these 2 classical bits to Bob. Right, so these are 2 bits of classical communication. Nothing fancy here, just a bit A is going to send over the channel, the classical channel, and a bit B is going to be sent over the channel. And these 2 bits are going to tell Bob what he needs to do to his 1 remaining qubit to get phi. And I need to tell you what's happening here in the picture, of course. And the way to analyze this is to kind of write down the 3 qubit state that we have at this point in time. So before Alice measures. So, and I'm not going to write out the calculation, but by now you know how to do it. You just start with the initial state and you kind of painstakingly write down what happens with the different operations the circuit tells you to do. So you do a C0 on the first 2 qubits, you do a Hadamard on the first qubit. What 3 qubit state do you get? I'm just going to write it down for you. So the state at this point so at this point in time, after the C0 and the Hadamard have happened on Alice's side, you can write it like this. 1 over root 1 over 2, 0, 0, alpha 0. Okay, I'm going to go a little bit low again, I'm sorry. Okay, this is a complicated looking 3-qubit state that I wrote down here for you, and you just have to trust me that if you start with a state which is a tensor product of the qubit phi with an EPR pair, and you do this operation on the first 2 qubits and this operation then on the first qubit, that the resulting state with these 4 lines, that this is the resulting 3-qubit state that you get. Okay, so this is what happens just before Alice measures her 2 qubits. And you can sort of see what will happen if she measures her 2 qubits, right? Those are the leftmost 2 qubits in the state. You can see the 4 possible measurement outcomes that Alice can get from her measurement. You can see them here. Right, so what will happen is that you will probabilistically collapse, or Alice's measurement is probabilistically going to collapse this 3-qubit state to one of these 4 lines. Right, let's consider, for instance, that Alice gets measurement outcome 0 and 1. That means that we are here. And if Alice gets measurement outcome 0 and 1, Bob's qubit will look like this, which is not quite phi, but it's sort of like close to phi, right? Like if you look at this qubit here, what do you need to do to reproduce the original phi? Which gate do you need to do? Right, if you compare this qubit with this qubit, the only thing that's different is that the ket 0 and the ket 1 have been interchanged. So how can you correct for that? You use an X gate, exactly, right? And how does Bob know that he needs to do an X gate? It's because Alice actually told him the classical measurement outcomes. So if Alice's communication says, well, you know, I got measurement outcome 0 and 1, at that point, Bob knows that he needs to do an X gate to recover phi. Similarly, if Alice got measurement outcomes 1, 0, the state looks like this, and in that case, a Z gate is going to do the right correction. If Alice's measurement outcome was 1, 1, then Bob in fact needs to do both an X gate and a Z gate to correct, to get back to the original phi, right? But these 2 bits that Bob receives from Alice, these 2 classical bits, they tell Bob exactly which correction operation he needs to do on his qubit to recover phi, right? So that's this piece here. This is just doing an X gate if A was 0 and doing a Z gate, doing X gate if A was 1 and doing a Z gate if B was 1. That actually does all the correction that is needed. And what comes out on Bob's end is indeed the qubit phi that Alice started with. And it has been transferred perfectly, like these infinite precision amplitudes alpha 0 and alpha 1, they have been transferred perfectly. And the only thing that went over the channel is just 2 bits, 2 classical bits of information. And mathematically, this is not hard, but it's sort of mind-boggling to think about what happened here. Like, we're sort of solving a seemingly impossible task by giving Alice and Bob access to one EPR pair, even though the EPR pair has nothing to do with the task that they're trying to solve. The EPR pair has nothing to do with the 2 amplitudes alpha 0 and alpha 1. So this is teleportation. Any questions about this? Yes, please. Okay, let me repeat the question. How do both have access to all the 3 qubits? That's the question?
Yes.
So the answer is they don't, right? This dotted line here, the stuff above the dotted line, Alice has access to it. The stuff below the dotted line, Bob has access to it. So there's no point in time where the 3 qubits are accessible to both. Well, maybe at the very end, but there Alice's qubits have already been converted into classical bits. And Alice gives Bob access to those classical bits by just transmitting them over a classical channel. Right? So what goes over this channel? Just the classical bits A and B. But at this point in time, you know, at the beginning, Bob has one qubit. He cannot access Alice's qubit. Alice could be light years away. Yeah, and notice why it gets changed, right? What we have at this point here is a rather entangled state over 3 qubits. And that means that the measurement that Alice does on her 2 qubits actually has some effects on the 3rd qubit. And in fact, the effect that it has on the 3rd qubit is that it will be put in one of these 4 states. And Alice is actually going to tell Bob which of the 4 states it is, because that's exactly what her classical measurement outcomes say. So these 2 classical bits of information, they tell Bob exactly, look, we are in this line of the 4-line superposition, or we are in this line of the superposition. And Bob knows which correction operations to do to his qubit to recover the original ket phi. And notice also that the phi that used to be on Alice's side, it has disappeared. We are not violating no cloning here. We don't have 2 copies of phi. Alice has lost her copy of ket phi in the process. Also, the EPR pair is sort of used up in the process. It's also gone at the end. Yes, please.
What having a quantum channel, isn't that kind of what they do through the EPR pair?
Yeah, you can think of this as simulating a 1-qubit quantum channel by consuming 1 EPR pair and 2 classical bits of communication. So indeed, you can think of this as simulating a quantum channel. But I'm never assuming a quantum channel, right? This is not some whatever telephone cable or something where I can send photons. It really is just like classical information. You can send it over a classical radio channel or something like that. There was another question, yes?
Yeah, I'm a bit confused about the measurement process.
Yes.
What actually is Alice measuring? So you have 1 state, you have 1 shot, you can even say.
You should keep in mind that what she's measuring is qubits, right? The state is made out of qubits.
Yes.
And to be concrete, think of every qubit as 1 physical system, like an electron. Then what is involved in this state is 3 electrons. 2 of them are held by Alice, 1 of them is held by Bob. Exactly. What Alice does is she measures her 2 electrons. Are they 0 or 1?
But doesn't she just gets a probability that it is 1?
Correct. I mean, there are 4 possible measurement outcomes here, like the pair AB could be 0, 0, it could be 0, 1, it could be 1, 0, it could be 1, 1. This is probabilistic. 1 of the 4 will happen, each with probability 1/4. And that's going to collapse you to one of these 4 lines of the superposition. So what the measurement does is it sort of randomly picks out one of these 4 lines of the superposition. And it collapses the state to that line of the superposition. And the beautiful thing is that at that point, the first 2 bits, which are now classical, tell you what needs to be done to the 3rd qubit to turn it into a copy of phi. Yeah. Okay. So I have about 10 minutes left. Let me very quickly give you your first sort of quantum algorithm that has like a big separation compared to classical. And this is a so-called Deutsch-Jozsa algorithm. And the baby algorithm that I described before, you can think of it as the n=1 version of the Deutsch-Jozsa algorithm. This dates from 1992, by the way. This is a few years before Shor came up with this factoring algorithm. It's like in the early 90s, there was suddenly this sequence of algorithms building upon each other, leading to Shor's quantum factoring algorithm, which was really a big thing. I'm going to explain it tomorrow. And this was the first in that sequence, or well, maybe the Deutsch algorithm was the first in that sequence, but this is a more important thing because it gives you an asymptotic separation, like where you can really say my quantum algorithm is exponentially better than my classical algorithm. And the setup is the following. It's a totally contrived computational problem that we're going to solve here, but that's okay. I just sort of want to establish the principle that there are computational problems that quantum computers are very good at. So here's my input. It's a sequence of bits. Capital N equals 2 to the little n. And each xi in this sequence is just a bit. The way I can access this is very similar to the baby algorithm. And again, if you don't like it, suspend your disbelief. We have a unitary. Let me call it O sub x. O for oracle, and the subscript is because it depends on x. And what it does is it maps basis state cat I, which is like a sequence of little n bits. And you can think of that as an address pointing to one of the bits in this sequence. So this corresponding Well, I wrote the letter I, so I guess I don't have to repeat that. What this does is it maps ket I to a plus or a minus ket I, depending on whether xi was 0 or 1. So if xi was 0, the basis state ket I goes to ket I. If xi was 1, the basis state ket I goes to minus xi. And you can sort of think of this as a quantum sort of random access memory where you can access the different bits in your long sequence at your choice. And you get the value of these bits as a sign in front of the amplitude. If you don't like it, don't worry about it. Again, the main thing I want to illustrate is the interplay of superposition and interference in a much bigger problem, like a problem that's not of size 1, but that's of large size. And we are being promised something about this sequence, which is that either all the bits are equal, so case 1, all the bits of x are all equal. They're either all 0 or all 1. This is called the constant case. Or half of the bits, half of these capital N bits, are 0. And the other half then has to be 1, of course. Half are 1. And this is called the balanced case. And the goal is to distinguish these two cases as efficiently as you can. And just an aside, like the little problem that was solved by Deutsch, by the Deutsch algorithm, by this baby algorithm that I described in the previous hour, that's just a case where little n equals 1. So the Deutsch algorithm, right? If little n equals 1, it means there are 2 bits in this sequence. The constant case means that the 2 bits are equal. The balanced case means that the 2 bits are distinct. And that's exactly the sort of the little toy problem that our Deutsch algorithm solved. So I want to give you a generalization of this to something where actually the number of qubits is not 1, but little n. So claim every classical algorithm for solving this problem has to look at least capital N over 2, in fact, strictly more than capital N over 2 of the bits. Right, there's capital N bits in our inputs, and the classical algorithm has to look at more than half of them to be able to see the difference between the constant and balanced. Yes, please. Yes, deterministic. Let me add that here. So something that has success probability 1. So every classical deterministic algorithm is going to have to look at more than half of these bits, and you can sort of see why this is the case, right? If your classical algorithm looks at let's say capital N over 2 of the bits, and it sees that they're all 0, that's still not enough to distinguish the constant versus balanced case, because it could be that the other half of the bits that it hasn't looked at are all 0, then you're in a constant case, but they could also be all 1, and then you're in the balanced case, right? So that's sort of an informal proof of this classical so-called lower bound for this problem. Like, this problem is very hard for classical deterministic algorithms. They have to do an amount of work that's proportional with capital N. Claim 2 is there is a quantum circuit it's called the Deutsch-Jozsa algorithm. I'll describe it in a second. That solves this perfectly with probability 1. Using one call to this OX operation and order little n other gates, so things like Hadamard gates. these operations on 1 or 2 qubits, these unitaries, those are called gates. And you can think of a gate as like an elementary operation. So if you have a quantum algorithm whose circuit doesn't use a lot of gates, that's an efficient quantum algorithm. Right? And the point here is that little n here is exponentially smaller than capital N. So this is an exponential improvement by quantum computation. This is exponentially better or faster or whatever you want to call it than classical. Right, in the simple Deutsch problem, we had the situation that a classical algorithm had to look at 2 bits separately, while a quantum algorithm just used 1 call-in superposition. Here, this difference is massively amplified. It's exponentially amplified. Let's see, how much time do I have now? Okay, let me spend 5 minutes explaining this algorithm, and then we can break for lunch. Okay, so here's the Deutsch-Jozsa algorithm. It starts with a bunch of zeros, little n of them. So we're working on little n qubits, right? That's the logarithm of the actual input length. We're going to put them all in a superposition using Hadamard gates. We're going to apply this unitary OX once. We're again going to do Hadamard gates. And we're going to measure our little n qubits, all of them. And now the claim is the following. In the constant case, the measurement outcome is that all of the little n measurement outcomes are all 0. But in the balanced case, the outcome could be anything except for the all 0 string. And that means that just from this measurement outcome, you can perfectly distinguish if you were in the balanced or the constant case. Okay, let me quickly trace the state as it goes through this circuit to show you why these 2 properties are true. Right, and then you have a full description of this algorithm, and you know why it perfectly distinguishes the constant case from the balanced case. So tracking the state through the circuit. We start with all the qubits being 0. When I write 0 to the n, by the way, what I really mean is a sequence of n zeros, like a basis state where the n qubits, the little n qubits, are all classical zeros. Then we do Hadamard gates to all of the qubits. And what that does is it puts this qubit in the plus state, it puts this qubit in the plus state, it puts all of the little n qubits in the plus state. And if you write that out, what you get is just a uniform superposition over all the basis states of n bits. So this gives you square root of 2 to the n, sum over, if we stick to the notation of my lecture notes, let's say all the i's ranging over the basis states of little n bits. I hope this notation is still clear, but this is just a uniform superposition over all the possible basis states that you could have on a system of little n qubits. That's what the Hadamard gate does. Then we apply this sort of funny operation OX, which in superposition allows us to look at the capital N different bits. What you get is 1 over root 2 to the n, sum over all I, minus 1 to the xi, ket I. Right, so in superposition, we're sort of looking at all of the bits simultaneously, all of the capital N bits, but each of them only with a tiny, tiny amplitude. because each basis state cat I has only an exponentially small amplitude in this state. So you're looking at all the bits simultaneously or in superposition, but each of them only with a tiny, tiny weight. And now we do this second batch of Hadamars, right? So I'm now at this point in the circuit. And now you get a somewhat more complicated state, which I'll write out for you. Okay, so applying the Hadamars to a basis state, a little n-qubit basis state cat I, gives you this basis state. I should explain the notation. Right, so this creates a uniform superposition over all basis state cat J with a plus minus amplitude that depends on the inner product between the bit strings I and J. This is a kind of a calculation you can do on paper to convince yourself. You don't really have the time to write it out now, but this is what happens if you apply the second batch of Hadamars. And this looks like an annoyingly complicated state that we have now, right? It's like a double sum over all the I's and all the J's. The trick for the analysis of the Deutsch-Jozsa algorithm is just to not look at this state as a whole, but only try to see what is the amplitude for the basis state that's all zero. So what is the amplitude for the basis state J, which is the all zero string? And that is relatively simple, because if J is the all zero string, then this plus minus 1 here is always just plus. So this amplitude is going to be 1 over 2 to the n, sum over all the i's, minus 1 to the xi, right? This is what happens if you look at the state and you only pick out the amplitude of the basis state, which is all zero. And here you can see what happens in the constant or the balanced case, and a beautiful case of interference is going to happen. So what is this number here? So let's first look at this amplitude in the balanced case. In the balanced case, half of the xi's are 0, half of the xi's are 1. That means that half of these signs here are plus 1, and half of these signs are minus 1. And therefore the sum is 0. So in the balanced case, the all zero basis state has no amplitude. And that means that if you measure it, you're going to get some other basis state, anything except for the all zero state, right? So that actually already proves this claim here. The all zero state has no probability to be observed as measurement outcome if we're in the balanced case. On the other hand, what happens if we're in the constant case? Then all of these signs are the same. There's 2 to the n of them, 2 to the little n of them, and either they're all plus 1 or they're all minus 1. Right? And you're dividing by their total number, so this is just plus or minus 1 in the constant case. Right? And if some basis state has amplitude plus or minus 1, and you do a measurement, you're definitely going to see that basis state, because the square of plus or minus 1 is just 1. Right? So in the constant case, the outcome of our measurement is definitely going to be the basis state 0 to the n, because its amplitude is all the possible amplitude there could be. It's plus or minus 1. And this concludes the analysis of the Deutsch-Jozsa algorithm. And let's just look at how efficient it is. The number of gates here is really just order of little n. And you're applying this sort of unitary lookup of the values of the xi's, you're applying it only once. Right, so really a big separation between an exponential classical complexity and a linear quantum complexity. And of course the downside is, well, there's two downsides. One downside is this is a super artificial problem that nobody cares about solving in practice. The other downside is if you allow your classical algorithm just a little bit of error probability, this problem is actually easy to solve. Because if you allow your classical algorithm a little bit of error probability, it can just, pick maybe 10 of these positions at random, uniformly at random, look at those bits, either they're all constant, or probably you will see zeros and ones occurring there, and you're in the balanced case. Right, so this is not a good example of something powerful and useful that a quantum computer could do, but it is a very nice example of the interplay of superposition and interference effects that in general is sort of the source of why quantum algorithms work. Okay, I think this is good time for a break. I think I probably went 10 minutes over time. Sorry about that. Any last questions before we break? Okay, so after the break, I will have 1 more hour of lectures, which I'll spend on the quantum Fourier transform and phase estimation. And then tomorrow, I'm going to explain the 2 most famous quantum algorithms, which is Shor's factoring algorithm and Grover's search algorithm. And there's also a little exercise session in the afternoon related to this stuff. Okay, thanks for being here. I hope to see everybody after lunch.